Go. And today's lesson, we're going to be looking at work, energy, and power. Okay, so I'm going to start off by sharing my screen to the formula sheet to explain to you what it is that you need to know for this particular section. Okay, just give me a second. There we go. All right, so on this particular section of work, energy, and power, there are a bunch of different formulas on your formula sheet that you need to be aware of. And I'm going to start by covering these because I think that they're the most important resource that you have. That formula sheet, if you know it correctly, can almost be like, I guess a little bit like a safety blanket. You know where to look, you know what you can do, you've got to cram less information into your head and you can work with it. So the first formula that they give here is the formula to calculate the work. And this can be work done by any force, okay? So work here is measured in joules. F is the force measured in newtons. Delta X is your displacement measured in meters. And we will go into what cos of theta is in much more detail just now, but it's effectively the angle between the displacement's direction and the force's direction. All right, so the angle between those is what we call theta. Okay, sorry, can I just ask a favor? I've got somebody who can't get into the room. Can you please send them the link that I previously sent to either lockdown group? All right, the next thing here that you hopefully remember from grade 10 is you would have worked out potential energy and kinetic energy previously. Potential energy I view as being the energy that an object possesses due to its height above the ground. So if I take my pen, my stylus, and I've got to be very careful because this is a fancy one, and I raise it up here, it's got potential energy because it can fall down and accelerate as it falls. So your potential energy comes about because of the height of an object above a surface. The potential energy is measured in joules. M is your mass, which must be in kilograms. Please, 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 physics, everything in kilograms, chemistry, everything in grams. Anything that you do in physics, you must do mass in kilograms. G is the value of 9,8. And please, I had a group of matrics about 5 years ago who decided that they could work with G being up or down and positive or negative, and they went completely crazy. So please, G is always just a positive value. Plug it in as 9.8. Don't think further about putting a direction with it. People do the funniest things in exams, even if they've never done them before. And H is what we call the height above the surface, and that is measured in meters. So that's our potential energy formula that we're going to use. I don't know of many schools that use U for potential energy. It is another unit, but I personally ignore that completely. So when I do this, I tend to ignore half of my formula sheet because it just adds too much, okay? Also, K is your symbol for kinetic energy. But once again, I don't like that. So over here, EK is your kinetic energy. Just in case you don't know, E stands for energy, and the K here stands for kinetics. That is energy that is kinetic. It's a half. M is your mass, which is in kilograms. Mara, do you have a question? Okay. And V is your velocity, which is measured in meters per second. All right. So I'm just quickly covering the equations that we're going to be using today. You will see I spend quite a lot of time on each of them. All right. Then we hit the next thing, which is the work energy theorem. And I tend to use this version. And I know that the change in kinetic energy is always the final minus the initial. So I personally don't bother with any of the rest of this. You're going to find even this one I hardly look at because I know that. So I'll view it as being that the network is equal to the change in kinetic energy. This symbol here we call delta, and it represents the change in something. And whenever you do the change in anything, it doesn't have to be kinetic energy. I think I even covered this idea with you when we did charge. That is always going to be the kinetic energy final minus the kinetic energy that you initially start with. So that is your network. And just so you know, this equation here, which is all of this thing, that is your work energy theorem. You are not forced to use the work energy theorem in a question unless they specifically tell you to do it. However, I find any question where they give me information and then they say, determine the velocity of this object at a specific position, this is my go-to formula. I tend to use this one before I ever consider the next one that we're covering because I really don't like the next one. All right, so just so you know, sorry, work energy theorem is not that one. A lie, I put my block around the wrong place. Work energy theorem is that one. There we go. So that's just the bottom part of it. So the work energy theorem here, ooh, is he playing? Undo that. The work energy theorem here, that one is your most common formula that you're going to be using. And as I mentioned, you only have to use it if the examiner tells you to. Otherwise, you can use any formula. Please note if they say use energy principles, you actually have an option of any of the ones on this particular sheet. Okay, I personally do not like using the formula of work done by a non-conservative force. Some of you may not know, but this idea of the work energy theorem was only introduced into the syllabus in 2008. So it was introduced to the syllabus after I matriculated. And I remember when they introduced it thinking, that's rubbish. How can you say that the net work done is only the change in kinetic energy? What about potential energy? And I remember getting really angry about it until I realized that part of this network is the work done by gravity. So we include the work done by gravity under the umbrella of network, and that's why it's okay. This version brings that potential energy or the work done by gravity out of the formula. So this is the work done by a non-conservative force. I'm going to get into what conservative and non-conservative forces are, but you can use this for work done by a non-conservative force. Okay. And then lastly, the two formulas that we use are power being work over time. And then I don't do that one because English is the average power is equal to your force multiplied by your velocity. So these are all of the little bits that we're going to go and look at individually just now. Okay, I'm going to take us back, as you'll have noticed I like to grade 10. I find that most of what goes wrong in matric is actually a grade 10 problem, which got worse through grade 11 and then fell apart in grade 12. So we're going to start by looking at mechanical energy and the idea of your potential and your kinetic energy. After I've looked at mechanical energy and those two aspects that make it up, we're then going to look at what work is, and we're going to link this formula to the work energy theorem. I'm going to touch on what conservative and non-conservative forces are and show you that using these two formulae give you the exact same answer pretty much every single time. I never use this formula. I can usually find a way, this formula, got to get rid of that. That's just going to confuse me. So this formula up here, that formula I go to more often than not, and then you'll see when you use power and link it to work, and when you use power and link it to force times velocity. Just for the record, this one here is way more likely. I guess it's way more likely simply because it's asked more frequently. All right. So I'm going to quickly stop sharing before I go to my whiteboard, and I'm going to quickly go to gallery view and just see all of you. Okay, quickly seeing who I've got here. All right, lots of you. We're up to 4 screens again, and it looks like they're relatively full screens. Okay, brilliant, and it's wonderful to see so many names that I recognize. Okay, brilliant. So let's get started again. When we talk about mechanical energy, so there's a question here saying, ma'am, which one is more likely, the potential energy? So when you say potential energy, I assume you're meaning conservation of mechanical energy, being potential energy, or the net. It's a very tricky one. I'd say that you probably, and I know this doesn't add up, but you probably got, I'd guess here, about an 80% chance of getting a work energy theorem. okay? At least 80% chance of getting a work energy theorem. And then the chance of getting a mechanical energy is much lower than that. All right, okay. All right, so there's just a quick question about the last formula. Let me quickly just jump into there. Sorry, got to go back. New share screen, share. Okay, so the last formula over here, just to quickly give you an idea, says it's the same as this. Okay, so it's basically power, but if you know that power is equal to work over time, and you look at this formula, which says that work is equal to F delta X cos theta. And we assume that cos is 0 degrees, which means that the force is acting in the same direction that the object is moving, which is kind of logical for most cases. Then we can shorten this to work as force times by displacement. So I can replace this W with this, and I get F delta X over delta T. So power is equal to force times by displacement over time. And I then take that bit out. Delta X over delta T is the velocity. And then we can say that the power is equal to the force multiplied by the velocity. Does that make sense? I just quickly need to check I didn't break up at all there, because I did see my internet symbol warning me that it was going a little bit wobble. Okay, so the reason that we put in the AVE for average is that technically these two can vary just a little bit, particularly when we're dealing with an object where we accelerate it from rest. So we could have something where we cover a certain displacement, but our acceleration is constant and we're going from a velocity of 0 to a velocity that's much bigger. Then it's much easier for us to count this as our average velocity. Because sometimes when we're accelerating something, it's got the same force, it covers a displacement, and we'll know what the fixed time is, but the velocity would have ramped up from a certain value to a higher value. So that's why we talk about average power. All right, so I'm going to quickly stop sharing that. Is it Diana? I've got to get this. Diana.
Yeah.
Okay, did that
Yes,
make sense?
A lot, ma'am. Thank you.
Pleasure. Okay, so please, everybody, I know that they're very big groups. We've currently got 180 people online, but that doesn't mean that you can't, in a fairly organized way, ask questions. So as long as everybody's kind of asking when it's appropriate, and ideally, if you type down the side, it's easier for me to decide when to answer you, but you're welcome to interrupt me as well. All right, so let us continue. Wrong share. There we go. Okay, so we were going to talk about the idea of mechanical energy. Now, many of you are going to go back to school after this and your teachers are going to curse me, but there isn't a symbol for mechanical energy. So there isn't like a uniform thing where everybody agrees we're going to call it this name. So because of that, I call it E-mech, personally. I know that there's some people who call it EM, and I'm sure if you were to go and ask your teachers to look at what you've been taught this a number of different ways. But we don't actually have to come up with specific formulas because we usually replace E-mech, or mechanical energy, with what it is, the sum of the potential energy and the kinetic energy. Now, to remind you, potential energy is the energy that an object possesses due to the height above a surface. Now, this is a very important idea to understand, that it's a height above a surface. So we care more about the change in height than where the actual height is. I mention this because there was a very hard question asked a few years ago where there was an object that traveled from here to here to here. And everyone freaked out because here to here there was no friction, I think. And down below there was friction. And they were given all sorts of heights, but you had to go from here to here and they gave you that height. And I just went and said, well, my potential energy here is mgh, and this height is this height, because I don't actually care how high it is above the ground. I'm calling this height 0, and I'm only working from here to here, and therefore I don't care what this bit is. So another way that I can describe to you what it means when we talk about the height above a surface is I could use the example that right now this pen possesses a certain amount of energy because it's a certain height above my table. But if I move this pen across to over here, where it's now off the table and above the floor, it can fall further. So I can't go and say that the height here of 20 centimeters wasn't correct, and suddenly the height there of 1 meter is more correct. So we pick a point as being a 0 height, and then everything above that is a certain height above it. Okay, I'm sorry, I can't tell you where the question is there. I literally do about 50 different questions from different papers every week with different students. So if you go back to the last 5 years of question papers, you'll probably hit it. I know I've definitely seen it a lot of times, so it's probably in the last kind of, even back to 2018, you'll probably find it. But it's a common question that they ask. So don't worry, it's the hypothetical here. That you could, if you're prepared to talk about the potential difference, this being point A and this being point B, you can work out or worry about how big that height is instead of worrying about the total height above the ground. Even if I use the example of this above the desk, then move across and this above the floor, my husband wouldn't be very proud of me, but if I went and got one of those, I think it's called a jackhammer, the things that can make holes in concrete, I could dig a hole further into this floor so that my pen could fall even further still. And it then becomes an immaterial thing because you can always dig a deeper hole. So the point is, when you're talking about your height, it's just the height above a surface, and you get to decide what that surface is or where it is, as long as you are consistent with everything when you're working out mechanical energy, that it's mechanical energy here, and that's the difference in height between those 2 points. So our formula here for potential energy is that it is mgh. I've already expressed to you what each of these are, but I'm going to quickly reiterate. This is mass in kilograms. If it's ever given in any other unit, please convert it first. G, we're just going to assume is the value 9,8. We're not even going to go into units or symbols. Plug in 9.8. Don't overthink it. And H is our height or difference in height measured in meters. This is our potential energy, and it's measured in joules. Our kinetic energy, I'm just going to do a different color here. Our kinetic energy, which I'm going to discuss over here, is the energy an object possesses due to motion. It will only have kinetic energy if it is in fact moving, which is why when we look at the formula, our formula is EK is a half mv squared. I know I got the squared and left the squared off in one of the previous things that we did together, but please make sure, once again, that's one of the most common mistakes that people make. All right, so over here, half is just a number. M is the mass measured in kilograms, and V is the velocity measured in meters per second. Now, one of the places where they can make this slightly harder is they can give you the velocity in kilometers per hour, and you all hopefully know how to convert from kilometers per hour into or back into meters per second, okay? And the way that you do this to go from meters per second to kilometers per hour is you times by 3.6, and from kilometers per hour to meters per second, you divide by 3.6. Just the number 3.6. All right, let me quickly jump to the questions. Grams or kilograms for mass? Sorry, kilograms. If I said it incorrectly, it's always kilograms. Okay, so anything in physics, last lesson we did, we were looking at electrostatics, which is physics. We're still on physics. So kilograms, kilograms, all the way. Okay, all right, kilograms, because we're usually dealing with rather heavy objects. But if they give it to you in other units, make sure you convert. So if I told you that this object was traveling at 72 kilometers an hour, and they like to do this, it gives them an opportunity to quickly check that you know what you're doing. All that you do is you take that 72 and you divide by 3.6, And if you did that, you'd end up with an answer of 20 meters per second. All right. In fact, I find that the biggest mistake that I make with this, you may have seen me kind of get concentration face here where I wanted to make sure I didn't make a mistake, is that I know it's 3.6, but sometimes I have to think twice about whether I'm multiplying or dividing. So this example is the one that sticks in my head. I know that 72 kilometers per hour is 20 meters per second. That's the one example, I didn't even do that on my calculator, that I've memorized because it's a realistic value. All right, I've got a question. Where does the 3.6 come from? Can I just quickly ask anyone who's taking photos, quickly take a picture because I'm about to clear the screen. Okay, clearing all the screens. All right, so if I have 1 kilometer in a time of 1 hour, that gives me 1,000 meters in 1 hour is 60 minutes of 60 seconds. So if I do that, I get 1,000 divided by 3,600. And if we then go a little bit crazy with our dividing, divide, I have 1 divided by 3.6. So therefore, I can see that 1 kilometer per hour is 1 divided by 3.6 meters per second, or I can get that 1 meter per second is 3.6 kilometers per hour. So you can rather, let me undo that. So you can rather easily convert between the two. All right, okay. So I presume everybody is good with this. Now, with the idea of mechanical energy, the mechanical energy at any point is equal to the sum of the potential energy plus the kinetic energy, which means we'd usually say that it's going to be equal to the mgh plus a half mv squared. So my mechanical energy at any point can be determined using this equation. So at any point, I can work out what it is. Now, I run a bit of a weird analogy with this one. Sorry if Alex is watching. But with this, I consider it a little bit like I've got a total amount of money. Some of that money may be in the bank account, in my bank account, and some of it may be in cash in my wallet. So if this is the fixed amount of money that I have, and I go, let's say, for example, I've got 2,000 Rand. And we start off, and I've got everything in my bank account and nothing in my wallet. And then I go to the bank and I draw money. I draw 1,000 Rand. I still have 2,000 Rand. I haven't gone to the shops. None of it's been spent. We're conserving this money. But if I draw it and I now have 1,000 Rand in my hand or in my wallet, I can't suddenly say I've still got 2,000 Rand in the bank. It doesn't work that way. So what I need to realize is if the amount of energy you have is conserved or the amount of money I have stays the same, if some of it changes from one form to the other, the total sum of both of them must remain the same, okay? So mechanical energy, we're going to be talking about how it gets conserved. But at any one point, I can look at the combination of potential and kinetic energy at that instant in time. Here, I can't look at this kinetic energy and this potential energy because they belong to different points in time. So if I've drawn the money out of my account, it's not still in my account and also in my wallet. Okay, so please just make sure you don't do silly things where you convert it from one form to another and then still keep it the same. So very importantly, when friction or when there is no friction, when there is no friction, we can say that the mechanical energy of a system is conserved. If I don't spend my money, the amount of money I have stays the same. So the law of conservation of mechanical energy, it's very similar to the law of conservation of anything. And if you remember, we looked at the law of conservation of charge in the last lesson. So the law of conservation of mechanical energy says that the total mechanical energy of an isolated system is conserved. I know it's a little bit redundant because technically isolated should mean that there are no external forces, but I still like to say provided that no external forces act on the system. And those external forces that would cause us not to be able to say that the mechanical energy at one point and every other point on that object's motion or however it's moving remain the same is if there is an external force. And the typical external forces that you'd look at are, for example, applied forces. So when something pushes on something else, so this would be an applied force like a tension or a push, somebody putting energy into the system usually, or a frictional force where something removes energy from the system. So external forces mean things that are outside of the system. Very importantly, gravity is a conservative force. That means that gravity is not an external force. Your external forces generally tend to be non-conservative forces. And in fact, the definition of your conservative or non-conservative forces links to whether or not they depend on the path taken and also how they affect the mechanical energy of the system. So if something is a conservative force, the work done does not depend on the path taken, only on the start and end point. And if we're dealing with the non-conservative forces here, very importantly, the work done does depend on the path taken. Okay, so for example, friction, the further a distance you cover, the more energy you lose overcoming friction. Okay, I'm just quickly checking. I'm very careful. I would recommend that you don't leave the second part of this law off. I know that it's redundant if you fully understand what isolated means, but I'd still be cautious to go and check the formula sheet and make sure that yours looks exactly the same. Sorry, just quickly checking things. Conservative forces is not external. I believe you can. That's cool. And what does it mean by the path taken? All right. So just quickly, Abra, the conservative forces, I tend to think of conservative forces as ones where you do not depend on the path taken, but it also is that they don't impact the mechanical energy. And yes, in fact, I wouldn't regard them as being external forces. External forces for me are things pushing, things pulling, and air resistance or friction slowing things down. Okay, so just a quick question from Hamza. Does the definition in the exam have to be verbatim from the exam guidelines? If you want to be guaranteed of your marks, I would definitely learn them off by heart. It makes it much easier for the examiner. I don't mark physics, I mark chemistry. But I can tell you from the chemistry definitions that we've had to mark, the ones that go on the formula, on the answer and memo sheet are the ones exactly out of the guidelines. And it makes it so much easier for me to decide to give you the mark if it looks exactly the same. But we mark it concept perfect. So if you don't use the right, exact right word, but you describe the concept perfectly, then we can give you the mark. All right, quickly jumping back to Kyle's question about the path taken. So can I clear everything from here? Everybody just quickly take a snapshot if you need to. Okay, so if I do the example, this is the kind of version. If I say that we go from here to here, okay, I would work out the amount of work done by a conservative force even if the force or the object's distance, if it went all the way around here, you wouldn't get a different answer. So you would get the line that's drawn in black would be the version that you did regardless of which path you took. So I've seen one question where they have, how does it work? A skateboard ramp. You've got a skateboard ramp from here to here, and the guy starts off at the top on his skateboard, and he ends up here on the skateboard, and he goes along the path here. And then they talk about the same question where they stick a plank over the arc, and he goes from here to here. Now, if the force that we're looking at is conservative, it doesn't matter whether the skateboarder goes down the arc or whether the skateboarder goes across the plank. Whatever that force was will do the same amount of work. So a typical example of a force that does the same amount of work is gravity. And the reason is that your displacement from here to here will be exactly the same. It'll be the same vertical height that you do work against gravity. If we're dealing with friction, which is a non-conservative force, you would probably have a shorter path going directly. And depending on whether these are made out of different materials or not, you may in fact have more or less work being done by friction depending on which path it was and what surface it was on. If these two had exactly the same coefficients of friction, blah, 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 you may find that the shorter path where we stuck the ramp over the top, or the whatever it would be, plank over the top, would have less work being done by friction. Okay. Just quickly, hold on, guys, you're putting in lots of questions. Okay. So distance is a non-conservative displacement. Nope, Kim, you're getting confused. You should link conservative and non-conservative forces to what the force is and whether it depends on the path taken or not. I know looking at it, it looks like I'm talking about distance and displacement, but I'm actually talking about whether it matters from where you start and finish, or so whether the path that you take makes a difference or not. I know how you're linking them to distance and displacement, but it's not a good idea. Okay, all right. And normal force wouldn't be conservative. Whew. We usually find that no work is done by the normal force because of the fact that it always acts at 90 degrees. Okay, so because a normal force acts at 90 degrees, we usually don't consider normal force as being either conservative or non-conservative, because normal forces don't cause objects to cover displacements at all, so therefore they don't do work. But I've got to get back to that. Okay, I'm jumping ahead here. Would I focus on the distance from the starting point till the end point? It depends on the individual question. Okay, usually, everybody, just quickly before you get totally paranoid, we can work out this distance provided it's a straight line. As soon as we're dealing with anything that's a curve, you can't work out the amount of work done depending on how far this path is. So usually, to work out the amount of work done by any force applied across a curved path, you either have to use W net is the change in kinetic energy, but you may not use W is equal to F delta X cos theta. This here requires delta X to be a displacement, which goes across a straight line. All right, so I think I've confused a couple of people, so I'm just going to pause. I'm going to ask you to keep these questions right now that you're asking for later, because I think they're jumping a little bit further ahead of what I've said. Okay, so with the conservative and non-conservative forces, there's a much easier way for us just quickly to kind of cover what that is. And that's that I'm going to tell you what the examples are, and then you'll hopefully not be too worried. Okay, so if you ask me what a conservative force is, technically there are two, but there's only one that you really count, and that's the force of gravity, which is known as weight. Some people get very caught up about the fact that you can have certain conservative forces, which are explosive forces, like where you get a spring and it discharges, but that's not what we're going to be asking here, so you can ignore it. Okay? Our examples of non-conservative forces, and these are limited to the ones that you're likely to get examined on, are friction, applied forces, and tensions. So yes, I do know that they overlap almost directly with what I told you before about the internal and external forces, but I don't want you to think of them as overlapping that way. I just want you to think of the fact that they both happen to fall into the same categories. All right, so don't make rules where there aren't standard rules. Okay, don't make them up. You're going to make things confusing. All right, so jumping back a step, so we've been jumping around a little bit. I want to just quickly cover an example, and you'll notice that this particular example of law of conservation of mechanical energy is the same idea that you often get examined on in momentum. So if what we're doing now helps you to answer momentum questions, that's fantastic. So I either like to test this with a roller coaster. Okay, so here's a roller coaster, and I might tell you that we've got a roller coaster up here, and it has a mass of 2,000 kilograms, okay, and it's traveling at 3 meters per second, and it is 10 meters above the ground, and I may tell you that the lowest point that the roller coaster reaches is over here, which we're going to say is on the ground, so it's at a height of 0, so this was a height of 10, and I may ask you what is the velocity or speed of the roller coaster at that point. So the rule that we're going to be using here, I'm going to call this position A there and position B just because it makes it neat. You're welcome to also use initial and final. So I'm going to say my mechanical energy at point A is equal to my mechanical energy at point B. Mechanical energy is potential energy plus kinetic energy at A is equal to potential energy plus kinetic energy at B. I'm going to give you the good news just now, which is equal to mgh at A plus a half mv squared, all at A, equals, oh, I should read A, equals mgh plus a half mv squared at B. Okay, now here's the good news. Any one of these three gets you the mark. You do not need to put in all three. I am a creature of habit, and every single time I put in all three, but if I had to commit to it, the last one is, I feel, the most important one because it tells you what to substitute in. So I was going to recommend, if you're going to be lazy, because you know that you only have to put one of the three in, please put in the last one. Just makes it neat. Then what we're going to do is we're going to plug in our values. Now we're looking for the velocity at B, so that is the value that we're looking for. Believe it or not, we know everything else on this graph. Now not graph, on this picture. Something else that's important is I don't actually have to tell you the mass. A lot of people get very scared in a question like this. If I just tell you, there's a roller coaster and it's doing this, what's its velocity? And you go, oh my gosh, I don't have the mass, I can't do it. So you throw away the marks. I hate to tell you, but since there's an M there, there, and there, the masses are going to cancel out. If you are scared because you don't know what the mass is, just stick in a value M and trust that it will make itself go away. You'll be able to cancel M from both sides and it'll be gone. Okay, so I'm just warning you about that because a lot of people get very worried on those questions where they don't get given a mass. If you don't get given a mass, the masses will actually cancel and they'll make themselves go. We're going to do this properly, so we're going to plug it in, but I could just as easily put any number here and I'll get the same answer. M times 9.8 times 10 plus a half 2,000 times by 3 squared. Now, before I go any further, I want to just quickly discuss a bad habit that people get into. They come up with this silly rule that says potential energy at the bottom is equal to kinetic energy at the top, and then they change the formula to just be EP is equal to EK. So EP top equals EK bottom, and they're so proud of themselves because they're sure they're going to get all the marks. There's no rule. No law of conservation of potential energy at the top is kinetic energy at the bottom. If you take this shortcut and you don't bother writing out this and substituting in everything, including even if this was a 0 here. So if this we knew was 0, I know that doing this will get you the right answer. I also know that it'll get you absolutely no marks. So please, this is one of those cases where being lazy isn't actually being lazy, it's being stupid. Okay, so please be very careful. You substitute in everything. If you've got a value that's 0, You put in a nice round 0. I'll in fact make this into a 0 to show you how it should look. You put in a 0 because if you don't put in that 0, you will lose your substitution marks. We get that fussy about zeros being substituted in. We know that zeros cancel away and they disappear away, but it doesn't mean you can't substitute them in, or you can skip it. So here we've got our mass. G is still 9.8. The height above the surface here case in point, is 0, so I put it in. I don't go, oh, I'm so smart, I know this, I'm leaving this line off. Put it in if you want your mark, and that gives you a half 2,000 multiplied by V. Don't forget to square it. Okay, so we'll have 2,000 times by 9.8 times by 10 plus a half times 2,000 times by 3 squared. And provided, you're going to have to shout if I've messed up my calculator. I got an answer of 205,000. I'm not going to repeat the calculations because I don't want to waste time. That's 0 plus 1,000 V squared. Okay, I'm assuming I got that right since nobody's yet corrected me. And I'm assuming you're all doing this at home as well. So 205,000 divided by 1,000 gives me that V squared is equal to 205. I square root both sides, and I get that the velocity at B, you can write a subscript, you don't have to, it just makes it easier to know what you're doing. Is there someone telling me I've got it wrong? Okay, so yes, I'm just quickly answering a question that's come in. I didn't get it wrong. You only use this formula, mechanical energy at one point is equal to mechanical energy another, if you are told that there is no friction. This is by far the easiest thing to use if you're told that it's a frictionless surface. Sometimes they hide the word frictionless in a word smooth. Smooth. Smooth is frictionless. Rough, friction. Okay, so my answer here is 14,32 meters per second. All right, and I could, using this equation, work out the velocity or height at any other point knowing everything. Okay, very important question that I've just received from, I've just got to check who it was, Kulani, was can we leave the answer in surd form? Absolutely not, okay? You don't leave it in surd form and you don't write it as a fraction. So if I look at this, I could get a surd answer of 205, no marks. Similarly to sometimes you'll get an answer of √3/2, no marks. And even if you ended up with like 20/31, no marks. You've got to write 20 divided by 31 equals. We're not maths teachers, we're science teachers, and we're really fussy about it. So this would become 0.65. That has to get converted. So please, I know in maths, they're quite often a lot more lenient about, oh, they wrote it in surd form or they weren't rounding up. You round for science. You write it to a minimum of 2 decimal places, but you always will write, let me just get that on, you will always write that answer. You've got to push your surds to decimal button over there and get the right value because we're not particularly sympathetic to it. All right, can I clear everything from here? Let me just quickly go back. All right, so I'm going to presume that most of you understand the idea of your, yes, Skylar? Okay, but I had a question from Skylar as well, but I'm going to go to Nisha's because I can read it. Can we simply write 0 if we know the kinetic? No. Nisha, there is a possibility that if you substitute in a 0 instead, so if you've got a value that's a half 2,000 times by 0 squared and you know it, that there is a small chance that they may not penalize you, but they're fully entitled to take away that substitution mark. Whenever I do marking, the examiner tells me specifically that if this just becomes a 0, there are no marks. There are times when it sneaks through, but sneaking through is the exception to the rule. And to be honest, to throw away a mark, I wouldn't risk it. I definitely wouldn't risk it in a matric exam. There's no point in not doing that extra substitution to make an examiner happy. All right, don't stress. Everybody the first time puts their hand up by mistake. All right, and then the question says, Rebecca, Rebecca says the formula is, so this formula only works for conservative. That includes applied force. What will push the object to move? Okay, So usually what will cause the object to move from one point to another, like on our roller coaster, is that at the top, it's got lots of potential energy. And as it moves down here, that turns into kinetic energy. So it's a typical rule that we can kind of go, you'll have lots of potential energy due to height above the surface at the top and kinetic energy at the bottom. What causes that object to move? Gravity. The force of gravity is what causes it to move when we're dealing with situations where there's no external force. So anything where we're assuming a law of conservation of mechanical energy, the applied force that gets that object to move is gravity. So if we look at a pendulum where you have a mass piece on a piece of string, you could even do this. Some of you may have seen swing balls where they have tennis balls on a string. You could get it to form or swing in a nice neat arc. That arc is because at the highest point, gravity will pull it down, causing it to speed up and reach its fastest velocity directly below. And then because it's got kinetic energy, which is energy of motion, its momentum will carry it upwards until it reaches the same height. Now, if we have a situation where there's no air resistance, so this over here is a pendulum just swinging back and forth like this. If there's no air resistance, which is an ideal situation, it will reach the same height every time. In fact, we usually wouldn't draw the height from there. We draw the height from the center of mass of the object, which is in its center. So we quite often talk about where the center of the object is rather than the highest point. All right. Okay, just quickly, there was a question here. If they tell us it's a rough surface, will they give us the coefficient of the surface's friction? It depends. In this type of question, it depends whether they actually want you to have to work out the frictional force from the coefficient of friction, which is quite a large amount of work. So usually in work, energy, and power, this section, we're not going to be focusing on how the frictional force comes into it. That tends to get examined a lot more in the Newton's laws section. But it doesn't mean it can't happen. So in this section, they can ask you to work out the work or energy done by friction. And from there, they can ask you to work out the frictional force. And once you've got the frictional force, they can ask you to work out the coefficient of friction, or the other way around. But it isn't something that I see very frequently. Okay, so can I quickly check before we go any further? Boy, we're getting lots of interesting questions here. If there's friction, will the mechanical energy still be conserved? No, Zoe. Mechanical energy relies on the fact that there's no friction and no external forces. Hey, Rebecca, for a pendulum question, there needs to be no air resistance. That is correct. So if you're assuming that you're going to be going and using this rule of your mechanical energy, I'm not going to go and plug everything at one place, is equal to the mechanical energy at another place, with mechanical energy being potential plus kinetic energy being constant, there can be no friction of any description. So you'll see it's no friction, no air resistance, etc. So no friction and no applied forces. Okay. All right. Is everybody good with this? I'm going to quickly stop sharing just for a second. So what we've looked at here is the idea of the law of conservation of mechanical energy and how you can convert potential energy into kinetic energy, provided that there is no external force. Okay, now just quickly, and I'm going to get this in now because I know I'm going to run out of time in the next little while. I will give you a break in just a second to stand up and shake yourselves out a little bit. But before we do that, I just quickly want to chat to everybody about Siavula. So many of you have already signed up for Siavula, but this is where you can practice what we do here. So I teach you the theory. We don't have enough time for us to practice 100 times and to iron out every one of your, well, 180 people here and 300 people on the group. So what I'm going to do is I'm going to rely on this platform to teach you the extra stuff that I can't do with you. So if I just quickly share this, this is just me showing you where to go into it. Okay, so if you go in here, www.siavula.com, okay, this is where you should sign up. It's completely free. Okay, so let me just quickly check. I am sharing my screen. No, it's changed its mind. There we go. So this is my thing, but what you'd do is you'd all go and I think you sign up somewhere down the side there, and then you put in your access code over there. But most importantly is the practice. So if you go to grade 12 science practice, okay, you earn all sorts of things as you do it, but you can jump in here, and we have just gone and done the section of work, energy, and power. So at this point, in fact, the section that we've done is grade 11, so it hasn't yet hit work or work energy, theorem, or power. So you'd have to go all the way back to grade 10 to do the section we've just done. But you can click here, and then it'll give you questions on specific things for you to practice. So here, if I were to be correct, we'd go into the grade 10 just to practice this idea. I know it's going a bit back, but sometimes going back makes more sense than going forwards. So there we go, mechanical energy. So here you've got things to practice on: potential energy, kinetic energy, mechanical energy, and conservation of mechanical energy. I'd say that conservation of mechanical energy is the most important idea. So here you can talk about two slopes and how they're going to have different kinds of energy, etc. So that's just to give you an idea of how you can practice the things that we talk about here so that you can make sure that you understand them properly. Okay. So because we're now kind of halfway in, and I know everybody gets a bit bored, can I ask everyone to quickly stand up and shake? Just kind of move your body a bit. Okay, I'm standing out of my screen while I do this. Just stretch those legs a little bit so you don't fall asleep on me. Okay, I know that it's a relatively long time. You can quickly run to the loo if you haven't already been doing that. All right, because we're going to carry on with the idea of force now, and then hopefully get through work energy theorem as well in this session. All right, sure, I'm just quickly running through who's here before we go. Lots of you today. It's lovely. Okay. All right, everybody back in their seats. Sorry, I know we probably shouldn't do a formal stand up and move break. I'm sure most of you have that, but I think it's still nice if someone reminds you to. Because otherwise you get so used to sitting in one spot that you forget and you doze off a little bit. All right, so carrying on here. We're now going to be moving on to the grade 12 new work. So we're going to be saying, all right, so you've just covered what happens if there is no external force. Now, what about if there is an external force? We can no longer say that we've got a situation where the mechanical energy is conserved. So how can we work out how much energy is either being put into the system or taken out from the system? And the way that we do that is using the formula W is equal to F delta X cos theta, where F is your force measured in newtons, delta X is the displacement covered by the object that's moving in meters, and theta is the angle between the applied force and the displacement. I find that a lot of people really struggle to get what this idea of theta is, so we're just quickly going to discuss it. And along with discussing what theta is, we're also going to start talking about positive and negative work being done. So imagine, let's imagine that I drew a line using a line. Imagine that you've got a lovely flat surface like that, and we place a box on top of here, and then we apply a certain force. Now remember here, it doesn't matter if this force is a push force or if this force, I'm just going to try and grab it, if this force is a pull force. So F can be a push or a pull, it doesn't make a difference to what it's doing. So we apply a push force, and what it does is it causes this object to move along the surface. So I'm just quickly going to, while I'm getting all smart and clever with making this thing move, I'm going to say that it moves from here to here. This is my delta X. So this over here is the size of the force F, and this is the displacement. So I'm going to go back, my clever skills. Probably going to move the marker as well, but let's try. And we push it. You notice the beginning of the box was on the mark? When we get to the end, the beginning of the box must be on the end of the mark. You can't push it all the way till where this is at the end, okay? You've got to push it till that point. So displacement is the direction between those two. So I like to say here that, well, the delta X went this way and the force went this way. So those two are technically in the same direction, which means that my value of theta is equal to 0 degrees. Whenever we've got the applied force and the direction that the object moves in being exactly the same, our angle is 0 degrees, okay? Now, what about if instead we have a scenario where Let's try and see if I can bring it back here. This object is going to be moving, all of it. This object is going to be moving forwards, but it's slowing down because there's a friction acting in the opposite direction. So I could also have a situation where there's a resistive force, but the object is moving forwards. So if I've got a scenario where this, I can't stop that little blue thing from moving through as well, but where this object here sorry, can everybody hear me again? Oh, good. I'm glad everything stopped for everyone. Whew, whew, I just blamed my husband for that. Told him it's because it's on the internet. I turned around and he is. So, all right, everybody back with us, I hope. Let's just quickly see. Okay, cool. And it's still recording. It looks like it's still recording. So, whew, done that to me twice today. Yay, I'm glad you're all back. All right, let's quickly go back and see if my screen is still there. Oh, it's taken away my pretty pictures. So let me just quickly draw those in again. Okay, hopefully that doesn't happen to us again because it gets very frustrating and scary when it does. All right, so just so you know, Kel, our internet at home is usually very reliable. It's just sometimes I think a lot of people are on Zoom at the moment, and I get very grumpy because we've actually got a paid for account here so that we can teach all of you. All right. So if there's a frictional force acting in the opposite direction, and this object moves from here to here, we're then in a position where the object is moving one way, but the force is in the opposite way. Let's not do that last step, but the force is in the other direction. So if we go back to what I had over here, which is W is equal to F delta X cos theta, then we have a situation where the force is one way, okay? Sorry, the force is the other way. The force is one way and the displacement is the other way. So our displacement is forward and our force is backwards. And I sometimes like to view this like that. The angle between those two is 180 degrees. So I can then go and say that my angle of theta is 180 degrees. Okay, so does everybody get with this value theta? If the two, the force and the displacement, are in the same direction, then theta will equal 0 degrees. If they are in opposite directions, then theta will equal 180 degrees. And if there's a component in the same direction, so for example, if I take this object, I'm just going to quickly move it back to where it started, and I'm now going to pull it across, and I'm going to pull it across with a force at an angle. Okay, so if this object, I'm hoping, let's put that cos back. If I pull this, I'm not going to be able to pull it across. If I pull this across, that will be my displacement, and my force acts that way. So we got the displacement this way, the force that way, and the angle between them is that angle over there, which we call theta. So when we end up with a situation, okay, where we have theta being 0 and then the same direction, we talk about this being positive work. And what happens is that the kinetic energy of the system increases. If an object experiences a force in that direction, it increases the kinetic energy. My up arrow means increases. If we end up with the force being in the opposite direction to the displacement, then we talk about that being negative work. And if it's negative work, then the kinetic energy of the system decreases. Okay, so now that we've kind of looked at this idea, I'm going to quickly give you an example, very quick one, where we just look at how much work is done by a specific force before we bring in the work energy theorem and put everything together. Okay, I'm going to presume that everybody is okay with that, and if you're not, you're going to speak up very quickly to let me know. Oh, there we go. Can theta ever be over 180? So no, theta isn't going to be over 180. If it's over 180, you're looking at it from the wrong side. So if I were, just quickly while I've got this here, if I were to be talking about, where are we? Undo. This bit here and that bit there, I'd instead consider that angle between the two. Okay, so we don't usually deal with the theta being any other angle between 0 and 180, but it can be any possible angle, but it just gets a lot more complicated. So we tend to view the inside angle and not stress about it. Okay, but you're going to find that this angle bit only really comes in when a tension's being applied to something at an angle. It's very seldom anything else. I mean, if we've got an object on an inclined plane, chances are that the force will be linked to the plane itself, the direction of the plane, because that'll be your displacement's direction, rather than where it's going compared to the ground, which isn't what it's moving on anyway. Okay, so let's just quickly do an example where we can plug everything in. W is equal to F delta X cos theta. So we're going to start off by looking at the work done by friction. In just one example. In fact, we can have work done by friction and done by other things, but I'm going to do just one at a time. So if we have an object on a flat surface getting pulled across, so here's my object, very straightforward, and this object, maybe I could even tell you it has a mass of 12 kilograms. It's not going to impact anything, but I can still tell you that. And it's being pulled in a rope that has a tension of 20 newtons. I could tell you all sorts of other things here, but since we only care about friction, we're only going to care about what the friction does. And it has a frictional force of 5 newtons acting on it. Okay, there's our frictional force. And this over here is an angle of 10 degrees, and the object moves through 20 meters. Now, I've put a lot of different information in here. So we're going to start by just saying how much work is done by friction. Please note, it may not look like it, but this frictional force is a horizontal arrow. I'm just going to quickly go and redraw it so that it doesn't look quite as wonky as it was. So that's horizontal to the ground. And then I can go and put on a little cap there. All right. So if I plug everything into this formula, I'm going to use W is equal to. Now, I personally like to tell myself or remind myself what I'm doing. So I say work done by friction because I want to remind myself. Just in case you don't know, friction is represented by a lowercase curly f. I know that some of your schools have got you into habits of doing F friction or F frick or F friction, but I'm letting you know that the official exam memos will have an F like that on for friction. So here I'm going to say the work done by friction is the frictional force. So I make that my fancy curly lowercase f, delta x cos theta. Can I ask, does anyone want to volunteer to answer this question since it's not, so that it's not just me? Any offers? Anyone brave enough? All right, if nobody's going to offer, I'm just quickly checking you are still there. Okay, you are still all here, good. I'm going to quickly do that. So I would plug in my frictional force. Now I know it's very tempting. You've got the tension and you've got other forces, but it gets to be too much. Okay, so just a quick question. I doubt that they're going to penalize you if you use a capital F and a small f to represent friction in your finals. I think they accept a wide range of them, but I'm just letting you know that this is what I use and that it is what the examiner uses, so it's okay. So here if we use friction, the friction is that 5 newtons. Yes, there's a 20 newtons, but that's going to be the work done by the applied force, not by the friction. Friction's only for friction. The displacement that this object covers is 20 meters. And the angle between the applied force and the friction, between the displacement and the friction, our displacement is this way. Our friction or our force is that way. So if you think about it, those angles make this cos of 180. Let's put that back down. I wanted to delete the other bits where I was drawing too many pictures. Okay. And that means that the work done by friction is going to be 5 times 20, which is 100, times cos of 180, which should give us negative 100 joules. Now, this negative means that it's lost. So that is 100 joules of energy that have been removed from the system. Okay, so negative here doesn't mean left or right. you've got to remember that with work, energy, and power, all of those are scalar quantities. So the direction is meaningless. It doesn't actually mean anything, okay? But here, this negative means that my system will lose some of its kinetic energy. All right. Now what I want to do is I'm going to do a similar thing where here we did the work done by friction. So this would be my work done by friction. Now I'm going to ask you to also work out what is the work done by the tension. So the work done by the tension will be equal to T delta X cos of the angle. Yes, Ahmed, would you like to do this one? Okay, just quickly going back, there's a question. So Ahmed, you're welcome to. You're just going to have to unmute yourself so you can speak. But first of all, there's a question here saying, why is it cos 180 again? They keep thinking it's cos of 10. Now it is going to be cos of 10 for the tension. But if you think about it, your friction acts this way and the displacement is that way. I should never draw these in the same diagram because one is a force and one is a displacement. So this is a mental picture that I have in my head. That's not a force diagram or a free body diagram. But the point is that they're in opposite directions. So you've got to remember that when we're dealing with the friction is acting straight back. Something else that's worthwhile noting. Friction always acts in the opposite direction to motion. It's the definition of what friction does. So friction will only ever give you a negative value. And one of the good reasons to make sure that you're aware of this friction always give you a negative value is I've seen questions where they tell you so many joules of energy are done overcoming friction and people put it in as a positive because they forget that it's got to be negative and remove energy from the system. All right, so we don't need to sub in the negative if the force is in the opposite direction. No, the negative, just quickly going back, can I ask everyone to just give me a second to get through the questions before you give me new ones? Okay, so subbing in the negative, you don't sub in the negative sneaks in through the cos of 180. So the angle is what creates the negative, not the force itself being negative. Okay, Brandon Miller, are we allowed to sub in -1 for cos of 180 and 1 for cos of 180? I would suggest I would never skip that step because you're substituting. If you think about the definition of what substitution means, you are substituting into the formula. If you do not put the angle into the formula, even if you get the right answer for it, we do not have to give you a substitution mark. We may be nice, but we don't have to. Okay, so just next question, will slow down. So when we are not working out the work done of the whole system, only the tension, the friction. For now, I'm only doing tension. Well, I've done friction, I'm doing tension, and then I'm going to link them together in just a second. And then there's one last question here saying, ma'am, what happens when you have cos of 90? Sneaky question, but no work is done. Okay, so if you have an applied force at 90 degrees to a surface, it does no work. Now, a good example of that is that this object has gravity acting on it. But gravity acts down, the displacement is to the side, those two are at 90 degrees. So if we consider all of the forces acting on this object, which I'm hoping to eventually get to, you'll see that anything that's got a 90 degrees for cos of 90 gives you 0, so you don't end up with work being done. So in this particular case, gravity does no work. All right. Can I continue? I'm assuming that's a yes because nobody's saying no. So if I go into here, there was someone who'd offered to do it or volunteered. Are they still there? Okay, Ahmed, can you speak up and unmute yourself? Ideally turn on your camera, but as long as you speak up, that's fine. Or type up. Yeah, there we go. Hello.
Yes, I'm here, ma'am.
Okay, brilliant. So what am I going to plug in for tension? Hello.
20 newtons.
Good. And my
we just take the
displacement?
standard magnitude.
Good. And my displacement? 20 as well.
Would
Okay,
be
maybe
sorry, 20 as is.
And then cos of?
It would be 10 degrees.
Cos of 10. And
10.
what's your answer?
393,92.
393,92 joules. And it's positive because the tension does positive work. It adds energy to the system. All right. Thank you, Ahmed. So over here, we've seen that we've got positive work being done by the tension because it pulls in the same direction as the displacement, and negative work being done by the friction because it pulls in the opposite direction. Now, this is how you calculate each of the individual work or works done by each of the individual forces. Quite often in an exam question, what they're going to start with is asking you to draw a free body diagram of all of the forces acting on the object. And one of the reasons we start with this is if we can identify all of the forces acting on the object, we can identify which forces can or can't do work. So when we draw a free body diagram, we represent the object as a dot. Okay, please note that little dot, typically I find mine is about 1 millimeter to 1.5 millimeters. Okay, so it's a little dot, maximum kind of 3 millimeters. If I draw all of the forces acting on this, a labeled free body diagram, I get friction acts that way, I get tension acts that way, and I must draw it so it looks like it, and I get gravity acting on this object. Just as a hint, there are no other forces. Velocity is not a force in itself, so even if this object were moving to the right and the only forces acting on it are friction and gravity, so there was nothing pulling it, you can't say that there's a force to the right because you feel like there should be one. An object moving doesn't mean there. All right, so do you measure the theta from the direction of displacement? Yes. So the theta is always the angle between the displacement and the applied force that you're talking about. Okay, yes, I must include normal. Sorry, haven't yet got there. Yeah, everybody on my case. Wonderful. I actually would have missed it. So we also have the normal force because this is on a surface. So your normal force is the force of the surface upwards on the object. Okay, so those are all of our forces. Please note, one of the ways that you can tell if you've missed a force is to look at the mark allocation. If this is for 4 marks, I very seldom have ever seen a question that's not got 1 mark per force. So if it tells you it's for 3 marks, make sure you've got 3 forces. If it tells you it's for 4 marks and you can only find 3, you've got to look for a last one. Please just be aware there's a direct link between the number of ticks and the number of forces and the mark allocation, always. Okay, do they give marks for the length of the arrows? No, they give you a mark for the direction, and it's not a bad idea to think about them in terms of proportion. So ideally, my 20 newtons should be longer than my 5 newtons. But if I then get very technical, this downward arrow of gravity should then be 120 newtons, so 6 times longer than, it gets complicated. So usually we give you marks just for the fact that it's there. Only if we've actually worked out every single value will we potentially ever do that. All right, could we break tension up into parallel and perpendicular? I would never do that for a free body diagram. You can, but it's messy. Inclined planes where you split up gravity into parallel and perpendicular components, that's the one that you can get away with, but usually in a free body diagram, we don't split up tensions. All right, so if we look at these and we imagine in our head, but don't write down on our page, that our displacement is that way, we can see that the normal and the weight are not going to do any work on this object because they're at an angle of 90 degrees. The only forces that can do work on this object are friction and tension, which coincidentally are the 2 things that we've worked out. Okay. Now, the reason that I've touched on all of this is this was my way of introducing you to the idea of how to calculate work. But we're actually going to use this as an example of how to apply the work energy theorem, which is W net is equal to the change in the kinetic energy of the object. So I might tell you that this object over here, I'm now going to go and take up my extra little diagrams that I've drawn in here that I don't need anymore. I'm not going to risk getting that one out. It's just going to be messy. I'm going to tell you that this object starts from here, with a velocity of 0 meters per second. Please, you can always do meters per second or meters per second, it doesn't matter. And I might want to ask you, what is its velocity when it gets here? You can't do this using conservation of mechanical energy because we've got friction the whole way across here. We know this because we were told what the frictional force was. So we're now going to solve this using net work is change in kinetic energy. Now I'm going to have to ask everyone, because I unfortunately need to remove the bit at the bottom here so that I've got enough work or enough space. I'm just going to make a little note here. The work done by the tension was 393,292. Got to be careful, 92 joules. and the work done by friction was negative 100 joules. Okay, the reason I needed to get that is I'm about to make it go away. All right, so if I continue from over here, I can say that the net work done is equal to the change in kinetic energy. Now, all of you guys remember when you did net force, so F net was the sum of all of the forces. Now, it is possible for you to actually replace W net with F net delta X cos theta. There's nothing to stop you from plugging in a net there, and working that way. But very few people ever do that. So very few people will ever work out the resultant of those two forces and then work from there. It's a very messy approach for me, at least personally. But provided you do it 100% correctly, you will get the right answer. Okay. So what I tend to do here is I instead view the network as being sum of all of the works done. I know I keep saying works. I know it's not correct, but it makes sense. So we've got work done by friction, work done by normal, work done by tension, work done by gravity. This is the one case where you do not need to substitute in the ones that don't do work. So I can say that this is the work done by friction plus the work done by tension is the change in kinetic energy. So it'll be a half mvf squared minus a half mvi squared. This was the bit, if you remember right at the beginning, I kept getting confused and pointing to this equation instead of that equation. Now's where I just show you that if you know change in kinetic energy, you don't need it. Okay, so how do I know which formula I'll use? As soon as they start asking me a question where they've given me forces and they're asking me about velocity and any forces. As soon as they've given me forces and asking about velocity, I know that I'm going to end up going into this formula. If they tell me specifically to use the work energy theorem, I also am going to. So the question here could be worded, this is just replying to Beth's question, could be worded as simply as use the work energy theorem to calculate the velocity of the object at position, whatever they've called this. Okay, so we know it starts from rest, and we know that it's going to a certain place and it'll gain that amount of kinetic energy and therefore end up with that velocity. So this question could be asked as calculate the velocity at this point, however they've labeled it, or they could say use the work energy theorem. I personally would use the work energy theorem even if they didn't tell me to, okay? Because in fact, with this particular example, there is no change in potential energy, so the answer is the same both ways. Okay, I'll explain that a little bit later, but I'm focusing on the two equations you need to be able to know how to do. Right, last question, and then I'm going to carry on. Would it still be accepted if you factorized out? Now, I'm going to caution you, Nazia, very carefully against this. It is possible for you to write this as a half m vf squared minus vi squared. The reason I don't teach it that way is that most people then get very silly and they go vf minus vi and their squared goes on the outside. And that's when it all falls apart. So I don't teach this as a rule purely because there's too much room for people who can't do maths properly to factorize it incorrectly and get it wrong. So my recommendation is always a half mv squared minus a half mv squared. Don't take shortcuts. Don't risk doing it incorrectly. It's just that if you're smart enough at maths, you won't have an issue with doing it either way. And it's much easier for me. I know where people trip. So I try to avoid teaching methods where I know they'll trip over them. Okay, so over here, the work done by friction is negative 100. The work done by the tension is 393.92 joules. We're going to have a half. The mass is going to be 12 times by the final velocity is what we're looking for. We want to know the velocity at that point, whatever they call it. And this will be a half. The mass is 12. And we need to know the initial. The initial was 0 because we started from rest, and I'm still going to square it. So if I have this value, I've still got on my calculator, minus 100, I get 293.92 is equal to a half times 12 is going to be 6 VF squared minus 0. Now please note, we didn't have to start with this being at rest. This could have started at a value, and all that you'd have done is plugged in that value and then subtracted it from the work. Doesn't matter that you didn't do that. Okay. I don't know if anyone gets that answer. We'll check in a second. So if I take that and I divide by 6 and I square root my answer, I got an answer without any rounding up of VF is 6,999. So my answer is VF is 7 meters per second, but I stand to be corrected in case I messed up. Yeah. Okay. So just be careful. There was a 6,99. Yeah. Okay. You changed to 7. So that's perfect. All right. The people that were posting their answers did get it. So what you would have to do in an exam, if you were asked this question, is they often wouldn't have laid it out the way that I did, where we started off and we said, okay, let's work out the work done by friction and the work done by tension, and then let's bring them all together. Sometimes you actually start from this point, and then you do work done by friction, work done by tension, and you kind of merge all of the bits together as you get there. All right. Can I ask everybody who wishes to quickly take a screenshot of the screen so that I can clear everything? Okay. All right. So what I'd like to do now that I've introduced you to how the work energy theorem goes, is we're going to quickly learn what the theorem is. Please note, this theorem, I'm not going to say is likely to be asked, it's going to be asked. Okay, you can come back to me if it isn't asked, then I'll say sorry, but I'd like you to plan for it being asked because there's a high probability that it's going to be the question that you ask. So the definition here for the work energy theorem is that the network done on an object is equal to, sorry, I'm growling, is equal to the change in kinetic energy of the object. And they'll quite often, when they ask you to define it, they'll say in words, because if they didn't, you could just write that formula, because that's exactly what it is. The net work done on an object is equal to the change in kinetic energy of the object. It's a relatively nice definition to learn, because provided you know what the symbol delta means and you understand what network is from WNet, you can just look at the formula and write down what you see. Okay, so just a big hint. When it comes to exams and questioning and how we do things and put them together, if I start by asking you to define or write down the definition for the work energy theorem, your big hint is we don't ask definitions unless you're supposed to use them. So more often than not, if I start with a write down the work energy theorem, that means that you're going to have to start using the work energy theorem. Now, I want to just touch on one last thing because I know we've got just a few more minutes left for today. We're going to be continuing with this when I see you on Thursday. Unfortunately, I'm not getting through quite as much as I'd like in each section. But the good news is this actually takes you majority of the way through the section. So we're well more than halfway. And so we'll do tying up loose ends and practicing. The thing that gets people on this particular section is gravity. Because gravity does not behave the way you think it should. So I want to just, before we finish off here, I want to chat to you about how gravity behaves and why gravity is different. So if I have a box and it maybe has a mass of 20 kilograms and it's moving up a slope here, okay, and I, for example, tell you that that's 20 degrees and I tell you that the height here that it goes up the slope is 5 meters, okay, and I then ask you to determine the work done by gravity, a lot of people do the wrong method. And this is where what I'm teaching you right now is actually the crux of what makes the difference between people who get this section and people who don't. So please note this rule applies even if we're considering a frictional force here and a tension here, and I'm only looking at the bit that makes gravity, but I can do that even if there are 100 other forces that we're looking at. So our rule was W is equal to F delta X cos theta. So the work done by gravity is the gravitational force, displacement, and cos of the angle. In this case, because I'm dealing with gravity, I put in my weight as the force. So Fg is equal to mg, which is 20 multiplied by 9.8, which I think is 196, but it's late enough that I have to check. Yep. It's 196. Then comes the bit that's special. We only ever use the height as our displacement. The displacement that the weight will work against is the vertical height, up or down. Whether it's being raised or lowered, we're going to put in the height here. And the cos gets a little bit tricky, which is why you need to think, but this is what we're going to be practicing on. This object has had a vertical displacement upwards. Gravity acts downwards. Gravity always acts downwards. Up and down are 180 degrees apart. So therefore, this will be cos of 180. And if I work this out, 196 times 5 times cos of 180 give me an answer of negative 980 joules. You will find that whenever an object moves up, the work done by gravity is negative. It'll always be negative because gravity always acts down. And if you're moving up, your displacement is up. Okay, was there a question? Somebody had raised their hand. If you want to quickly ask, you're welcome to. Okay.
Yes, ma'am.
Yes, okay, just one at a time. I think it's Divine first. If I've said that correctly, yes?
Excuse me, ma'am, can you please redo that part of the 180, how it's 180,
Pleasure.
please?
With pleasure. This is the hardest bit of work, energy and power. I will happily go over time for it. So, just wait a second. Was it Divine? Did I say your name correctly?
Yes, ma'am.
Good. So, Divine, which way does gravity act? Up or down? I know it's not a trick question. Which way does gravity act?
Gravity acts downwards.
Good. Non-negotiable, gravity acts downwards, always. If this object is moving, and we're only considering the vertical directions here because gravity only acts vertically. This object, you agree with me, it was on the bottom level and it's now on the top level. Has it moved up or down?
It has moved up.
Good. Now, our rule here is if these are in completely opposite directions, the angle between them is 180 degrees. If this object had started at the top and moved to the bottom, then its displacement would be down and its weight would be down. If they're both in the same direction, then we say that the angle is 0 degrees. So our rule is that if an object moves up, the work done by gravity is always negative. And if an object moves down, the work done by gravity is always positive. And the reason that I mention this to you is that if you didn't use the 5 and the 180, you guys get so confused as to how to bring the 20 in when gravity acts down, and suddenly you've got an object and you're considering this force and this, and then there's angles, and oh my goodness, it just blows your brain. Okay. In fact, I must be honest, it blows my brain to the point where I can't tell you how you deal with it if you didn't deal with it this way. It's that confusing. All right. So the theta for an applied force acting at an angle, a bra, when it comes to gravity, you don't deal with applied angles. Gravity acts straight down. So we can deal with tensions acting at angles, but when it comes to gravity, gravity is straight down. Okay, so if we were to consider this object, even if it was sitting over here on the slope, we're going to consider only the vertical height. If they don't give you this vertical height and instead they give you the distance here, you then cheat and you use sine as a ratio and you say opposite over hypotenuse and your angle, and you work out what that height is, because it's going to be easier than trying to do any other alternative, always. Okay, so the question here was, when do you use the 20 degrees? Not for gravity. You'd use the 20 degrees if maybe, in fact, no. You'd use the 20 degrees to get this height if they hadn't told you it. Chances are, with an object moving up this slope, the tension would act that way. Oh, sorry, that's not tension. The tension would act up the slope. the frictional force would act down the slope, and the displacement is in the direction of the slope. So you wouldn't really need to worry about this 20 degrees other than to work this bit out. And technically your normal is at 90 degrees as well, so your normal wouldn't involve the 20. The only place where that 20 degrees might come into is to help you work out this value of 5. All right, now I'm pretty certain that this last little bit that I've given you here is very likely for many of you to be a bit of a game changer. But as much of it as it is a game changer, it's something where you've got to practice it a lot before it actually makes sense as to how you do it. So now you've got an idea that you can do this to work out the work done by gravity, but it's going to be something that we're going to have to kind of work on when I see you on Thursday to make sure that you can apply it correctly. All right, so I'm not abandoning you. I know you need a bit more on this. Okay. So, ma'am, can you please explain what you said about the use of displacement in this example? What I said is that I'm not going to be using the displacement for when I'm working out gravity. It's specific to gravity. When I'm using the object moving up the slope here, I can consider this as my displacement when it comes to the friction and when it comes to the tension. Okay? But I can't use that when it comes to the displacement for anything with gravity. With gravity, the displacement that we use is always going to be the change in vertical height. It just makes it easier. All right, I can promise you that. I know it gets a bit tricky with this, but that's how it works. Okay, so I'm going to come back to this section again when I see you on Thursday. You can try and start practicing on this. You've got a wonderful tool in Siavula that you can use to practice in the meanwhile. Okay, and hopefully it'll make a lot more sense to everybody. Okay, I know I didn't do it last time, but I think I'm going to do it in my Tuesday lessons just for fun. Can I ask everybody that's still here to please turn on their cameras just quickly if you do have one? We will not judge you as long as you're wearing clothes. So I'm just going to quickly scroll across all of the screens so we can see all of the wonderful people that have been coming in here. And I'd like to thank you guys for taking advantage of this opportunity. It's very rewarding for me. But it's also wonderful to know that there's so many of you. I don't know if you're aware of this, but I'm in Cape Town and I've got students from Standerton. I grew up in Standerton at some point in my life, so it's absolutely amazing. There are people from Durban, there are people from Joburg, there are people from Lenasia. It's literally across the country, which is really, really exciting for me. So there are people, one day we're going to put up a map and you can all put a dot where you live so we can see how far we've reached. All right, have an absolutely, absolutely awesome evening, everybody. And I shall see you again on Thursday. Bye-bye.
Thank you, ma'am.